Hello, James. Good morning. Thank you
Good
for
morning.
finding the time to talk with us on the Rigging Bodies podcast. How are
hmm
you?
Yeah, good, thanks. Yeah, thanks for having me.
So, just as I usually ask to the all the guests, can you introduce yourself and talk a little bit about your journey and your career?
Yeah, happy to do so. Yeah, I'm James Jacobs. I'm currently the CEO and co-founder of Ziva Dynamics. Prior to Ziva, I spent more than 20 years in the visual effects and animation industry. A good portion of that time, like 8 years of that time, was spent at Weta Digital, where I worked there from 2004 through to 2010, and then again from 2011 through to 2013. Through the course of my time there, I focused on character. Like, we're actually my entire career, I've had a focus on character creation, starting on the artist side of things, and eventually sort of worked my way down to writing software in order to help make better results.
Oh, nice. So you're I mean you started as a developer. I mean you're an engineer or you like like self-taught and
Yeah, I always had, I enjoyed programming as a child, and but I didn't have I don't have any professional training in it, other than what the good fortune of being able to share office space with lots of smart people and pick up what I can. My professional training's more on the art side. I went to art school and went to film school, that sort of thing.
That's great. I mean, I know many people that does this path, and it's amazing. Like many of the like great development that is being doing on our area right now. There's many people that is self-taught and that they've had like a similar path on that. That
hmm
it's I think I feel always very interesting. Like something that you feel like very difficult when you're a child, like all the math and all the engineering skills that looks like impossible to achieve and
Yeah,
that
no, yeah, no, absolutely. Well, that, and I find having a goal, like if in the case of a character, like if you need to solve a certain problem with trying to make a character look a certain way, or like, yeah, in the case when I was a kid, I was sort of more focused on making my own video games, that sort of thing. That's a really great incentive for you to learn what math you need to in order to achieve those ends.
yeah, it's a very like goal driven like learning
Yeah,
experience and a very like project
yeah.
like bit centric, so you apply directly what you're learning, so I think it's a really great way to do it.
For sure. I mean, I have to say I do definitely appreciate the breadth of knowledge with, especially today with the team we've assembled at Ziva. Like we have multiple PhD holders on the team, and other people with advanced degrees, and it's great to be able to talk about these concepts and come up with solutions with people that have that kind of breadth, because they'll have exposure to certain approaches that I might not have encountered in my professional career. So it's good to have both, for sure.
Yeah, absolutely, of course. So can you talk a little bit more about Ziva and your company, what you do, and what are your products and services that you offer?
Yeah, happily. So Ziva was started in April of 2015. We're coming up to a 5-year anniversary. In the whole purpose of Ziva when it was started was to be able to create software, or empower people to be able to create super realistic characters and deploy those characters in the domain of their choice, be that for use in films or games or any other kind of interactive experience. So in order to make that possible, we had to write new technology, invent new approaches to do that. The only commercial-facing example of that we've created up until this point is Ziva Vfx. And Ziva Vfx is a plugin for Autodesk Maya, and is purposefully chosen because that was the target audience that we were trying to go for, and it represented the least amount of user adoption to go into a tool that everyone's already familiar with. And the purpose of that tool is to be able to accurately represent the anatomical physics of characters. So that was released. We went to beta initially in September of 2015. It was first used in February of 2016. The first Sony Pictures ImageWorks was our first customer. They used it early on in beta still for Suicide Squad and Ghostbusters. And then we came out of beta in the summer of 2017. So it was commercially released at that point. And since then, it's been used in lots of movies, TV shows, commercials, so on.
And so it was almost 2 years of beta from the first beta to the commercial release.
Yeah, people were purchasing it during beta. Like we had a couple big customers that ended up using it in that time period. Like ImageWorks is the first customer, and they bought a good footprint of it. And then Image Engine was customer number 2, and they'd used it on the first Fantastic Beasts film. And then we just we had a few others before it became official, and then once it was officially released, we started to take on new customers at a bigger rate.
Yeah, that's impressive. I mean, it's how much it takes to make one like product of this level of quality, that it takes 2 years. Like, to develop and release the final like release. It's it looks like, I mean, it's, if you think like in the scales of production, I mean, some movies takes less time to produce, or even video games, and
sure,
it's amazing.
Yeah, I mean, we certainly don't have the number of staff that you might have on a typical film, so that leads into it. But I mean, writing software like this, it doesn't scale the same way like maybe movie production might. Like there's if you throw more people at a software problem like the one that we're solving here, you hit a critical mass, and beyond that, things become less productive, not more productive. So we were happy with version 1 when we finally got it out. But when the company was first started, we built a list of what functionality the software we planned for the software to have, and I think like we're probably not even halfway through our list, but it's fully, we're beyond where I've been in the past as far as what capabilities were represented in proprietary software that I've been involved with working on.
So it's on the for instance, when you develop the software, the way that you have like these like goals for the release, like let's say X and B features that you want to go there, and then the list it's infinite basically. Like
it's pretty long.
And unless for my experience, if I mean, I don't think it can compare, but for your product, but when you go more and more, it's like instead of feeling that you reach the goal, the list becomes bigger than the goal looks far away than when you started.
Yeah, no, we're just getting started on a lot of things. It's I mean, we took advantage early on of grabbing a lot of the lower hanging fruit, and there's some really cool features that will be in future versions, but they like actually the animated rest shapes, which came in version 1.7, is a good example of one which wasn't a low hanging fruit, and so that was kind of like a really major feature that we spent more than a year working on in order to get it into the product. So like some of the things that we'd like to do, the amount of time it actually takes to develop it is over many months, over a year in some cases. And then other ones we can do within one release cycle, so within 3 to 4 months.
And for the people that are listening and doesn't know the Ziva Vfx, can you explain a little bit what's behind this technology and how it works?
Yeah, certainly. So Ziva Vfx is an elastic solid and sheet simulator. So what that means is if you're familiar with a cloth simulator, It's similar sorts of concepts, except we're not limited to dealing with thin sheets. We can represent solid objects. So like a steak is a good example of that. If in our software we sort of co-opted the language of anatomy, and for us elastic solids we call tissues. So a tissue like an anatomical tissue, and the default material properties match that of muscle. And actually I can jump over to a different screen. So I have Maya here, and I have the plugin loaded. It might make a little bit of sense for me to just demonstrate it visually. So I've created a sphere here. I'm sort of famous for doing tests with primitive objects, and they may not be the most compelling, but I find they're good for demonstrating what the functionality is. So if I have this sphere, if I go into the menu, the plugin's loaded, and you get these three new menus at the top here. There's the Ziva menu, the Ziva Tools menu, and the Ziva Transfer menu. So in the Ziva menu, this is all the basic functionality for building stuff. In the Tools menu are a bunch of things which help you build things. And then in the Transfer menu, as a name would imply, it's stuff that allows you to then take work that you've done on one character and then transfer it to other characters. So on this one here, I'm going to create a tissue. So I've done that. You'll see this like lattice work has appeared around the sphere, and we have this big custom locator, and that's showing us how small that sphere is. This is 1 meter, so it's a really small sphere. So I'm just going to scale down the locator, and that's the equivalent of scaling up the sphere from the standpoint of the solver.
So it's like a relative scale of the world.
That's right.
That's very nice. Because normally when we, I did some cloud simulation in the past, and with some of the solvers, and like exposing that clearly the scale of the world is. No, I mean, it's the first time I see something that is clearly,
it was
clear.
It was a pet peeve of mine with other software as well. So that's sort of why we put this in like this. When I hit play now, you'll see that's falling under gravity. So it's just like a simulatable object now. So if you want to do fun stuff with it, though, you need to interact with it. So I'm going to create another sphere. And I'm going to move it up above it. And the inputs into our system, we call them bones. So I'm going to turn this into a bone. So if you're familiar with with nCloth, I mean, this might be like a passive collider type thing, and this one would be your cloth object if you were to think of it in those terms. So I'm going to connect these two things together. So in Ziva Vfx, whenever you select vertices, it's just a shortcut for painting a map. So if I make an attachment here, if I were to look at this now, there's a painted map there that I'll just show you actually directly. So if I right click on this, and then I go to you see that there's maps affiliated with all of the different node types that are there. You see there's an attachment map. I can add more points, or I can remove points, or you can smooth the points and it will attenuate it. But I'm just going to keep it as a sort of symmetrical looking attachment like this now, because it will be good for demonstrating some of the capabilities. So if that's the coffee machine in the background. Sorry about that.
No worry. It's, I can hear anything, so.
Okay, so actually I'm going to give myself more frames to play with, because that's going to go by very quickly. So now if I go to interactive playback mode, you'll see it's a simulated thing now.
It's like a balloon with water.
Yeah. So the default material properties of this, if you look at a tissue, you have a bunch of little nodes that get attached to it when you instantiate it. And one of them is this Z material node. And on this one, you'll see a bunch of mysterious looking attribute names. And these are the engineering terms for these things, for the kind of the features of the way the dynamic material behaves. And we've chosen to go with the engineering description because then you could just go to Wikipedia, look up what the Young's modulus is of some tissue, plug it in, and then you'll know that the value matches what the real world one is. So that's the reason for that. The numbers that we deal with tend to be quite nonlinear because for something like gelatin, for example, or brain, it might be super soft. It would be like Young's modulus of 10 to the 0 with a value of 1 or something, or 5 or something. It's very, very soft. But then if you wanted to go to something as hard as diamond, it would be like a billion. So because of that, we've split up these attributes into 2 different attributes. One of them gives you a power of, and then the other one lets you just punch in a floating point number. So it's just to make it easier for you to be able to jump up and down stiffnesses easily. So yeah, the Young's modulus is stiffness. Poisson's ratio is the volume conservation. It's a specific implementation of how to do that. It's like a ratio of height to width for each of the tetrahedra, which this lattice work is built out of tetrahedra. They're the simplest three-dimensional shape that you can use to discretize a volume.
So it's like it voxelize, kind of.
Exactly, yeah. Except instead of cubes, it uses these tetrahedra to do it. And then the volume conservation is similar to Poisson's ratio, except it doesn't limit it to trying to conserve the volume of a single element. It can distribute the volume across neighboring elements. So it would allow, if you put this one to 0, for example, and put this one up, what would happen is if you squish one element down to nothing, it'll push its volume into its neighboring element. So kind of like putting your hand on a water balloon, and the water will travel from one side of the balloon to the other. And then mass density is what you'd imagine. It's just the mass and the density of that mass through this object. And then here are some extra attributes, like rest scale allows you to, as the name might imply, it allows you to change what the scale of the elements that we're solving are in its rest state. Kind of like changing the edge lengths of a mesh that's going into a cloth solver, but this is doing it on the tetrahedra. So it's not a physically motivated attribute, but you might find it useful for some situations. Pressure is a normal force pressure. So along the normal of the embedded mesh, like in the sphere in this case, you can put a pressure inward or outward. And surface tension minimizes the surface area of the object, kind of like how if you put release water droplets in 0G, they'll make spheres because that's minimizing the surface tension, which minimizes the amount of surface area that's exposed. So that's what surface tension does. So with all these things together, we can sort of help make creatures. But right now, so I got kind of into a lot of detail really quickly. So maybe.
No, I'm very interested, so I was like paying a lot of attention. So
okay.
Don't worry.
Okay, cool. So, I'll sort of go. Maybe I'll just sort of describe now how this relates a little bit. So, as you saw, when I turn this into a tissue, you got this TET mesh around it. So, under like everything else on the solver, it has the TET mesh generation has this affiliated node. And then it also has painted map. So you have this overall TET size, so it's that's the default there, but I can make them smaller if I like, or I can undo that. And typically, like you're looking to try to balance, because the bigger the tetrahedra are, the faster your solve will run. But you want them to be small enough in order to capture the frequency of deformation that you're interested in. So we've added this functionality that allows you to paint the resolution locally. So I could go in here and paint it like that, and you'll see that the TETs are small in that area but big elsewhere. So that's like if we were to do a naive implementation of what we're doing, you can see that since the TETs on screen left are sitting well outside of the embedded surface, and the ones on screen right are much closer, your natural inclination would think that this sphere would just drop and then rotate to screen right because you'd think there's more mass sitting outside of the object.
Mm-hmm.
But we're doing some extra math trickery in order to do this thing called volume fractioning. So that what that means is when I solve it now, it still falls straight down because we're aware of the volume that this embedded object is occupying, and it distributes the density and like mass density in the appropriate part of the volume. So it's not heavy outside. So that's kind of cool. And it allows you, a lot of the thought that's gone into what we're doing is we want to make it possible for people to iteratively improve and tweak what they're doing without having huge implications like on the output. Like, so meaning you could start with a really coarse tap mesh, block out what you're doing, and try to get things to work the way you expect. And then if you go in and make parts of it higher resolution, you don't want the overall behavior of the simulation to completely change, because then you have to go back and rebalance everything. So with Ziva Vfx, because we're using the finite element method, which is one of the continuum approaches, that in itself makes it easier for us to ensure that the fundamentals of the simulation don't change. And then by doing stuff like volume fractioning, it also makes it possible so that you can go in and iterate on the resolution of things you're working on, and then there aren't fundamental changes that make you have to rebalance the whole system. So it's a lot of focus has been on that area. We've also done the same thing as far as how we discretize time. We have multiple integrators, like backwards Euler is the one which we first used, and it's the most stable of all of them. It's the least, it dissipates energy really quickly. But we do have two more energetic ones, which actually give a more accurate picture as to what's actually happening. If this were a real thing, because you're not seeing numerical damping. So we have BDF2, which is second order backwards Euler. And then we have this one called TR-BDF2, which is trapezoidal and BDF2 interleaved. And this one's really, really nice because it maintains a lot of energy, but it's because it's doing this interleaving, it's surprisingly stable for what it is. And then we have Quasi Static, and Quasi Static allows you to solve not for dynamics but for energy minimization. So if you want to use the solver to, say, construct blend shapes, or as a modeling tool or something like that, you might want to use Quasi Static. I'll demonstrate that. You'll see with Quasi Static mode on, it'll just fall immediately, because you can kind of think of Quasi Static like, imagine you have an object, like say you have a water balloon in your hand, and you drop it, and it kind of will oscillate up and down. But imagine you held your hand there for 10 minutes. Eventually, the oscillation is going to stop, and the water balloon is going to come to equilibrium.
That's I see. So it's like if you goes to the final rest pose immediately.
Exactly.
Instead of waiting to the solver to lose energy until it gets to the rest pose, it goes straight to what will be the result if it's a rest pose.
Exactly. Yeah, that's exactly what it does. So that's really useful for some situations. So yeah, we felt it was important to include it.
Yeah, especially if you bake in some shapes from your solver back for in some situations, I guess for characters. Yep. It's convenient to have this bake if it's like background character or just for like a starting point for blend shapers or whatever can be on the production. Yeah, it's very, very convenient to have this final position.
Yeah, absolutely. So some of the other stuff. So yeah, I've shown an attachment, but I haven't shown. I'll show a material. So I selected this side of, and again, like everything else, this is just a quick way to paint a map. So I'm going to, in the Ziva menu, I'll add a material. And then if I look at the, let's look at the paint on that. So the material node here. You'll see half of it's painted white. And then if we look at material 2, you see this is stacked on top of material 1. And you can kind of think of it like in Photoshop doing an over. So like this one, where it's white, it's going to obscure the material underneath. So I'm going to make this one like a 100 times softer than material 1. So now if I run the simulator, you'll see, half of it's soft.
That's nice.
And then I'll just get rid of that material, and then I'll just show fibers really quick. And that's kind of like, there's more features in there, but that's probably enough to get the sense once I show fibers. So fibers or muscle fibers are like what a real muscle does. So rather than you'll have this fiber node on here now. So far I've shown passive tissues, so like the equivalent of like relaxed muscle or like a piece of steak or some fat. But if I have if I put a fiber on here, now I can flex the muscle like a real muscle.
Oh, like contract the muscle. So yeah, because this is one of the things that, especially if you try to do like a rig with some kind of muscle simulation using like maybe in cloth or another approach, this kind of tension, it's the thing that it's always difficult to do, because you always have the simulation, the jiggly part, let's say.
Yeah.
Okay, no, but when obviously the muscle doesn't work like that. When it's in a tension, it's not jiggle. It's very like tight and.
Yeah, no, and this has always been one of my pet peeves with like old school sort of muscle systems, like where they're really just a extrusion along a central curve, right? So it's a procedural model of a muscle. It doesn't really match what happens in the real world, other than the fact that it might do a volume conservation over the entire tube. And that so when you squish it, it will bulge, but it doesn't stiffen. It doesn't do any of the stuff that real muscles do, other than it might sort of resemble one visually, and they give it the name muscle, so people kind of think of it as a muscle. But so it was important for like Simon Clutterbuck and myself when we were working together on tissue at Weta to make that sort of big leap from having a procedural representation to doing something which acts more like the real world.
That's really. And I have a question. Maybe it's I don't know if that part is solved by the Ziva tools or but when you have the, let's say, your under structure with the bones and let's say the muscles thing that are contracting and behaving with the real world behavior. How do you attach the skin and because I remember we was talking of micro before, like I saw your videos when you was on Weta with the tissue. You explain how the fascia works and that it's not real like sliding the muscle under the skin, that it's something that you have like a tissue that shares and deforms, but it's not like real sliding that the people does. No, that's.
Yeah, if you sort of look at what sort of happens in a real body, I'm take this with a grain of salt because I'm not a doctor, but just sort of what I've sort of researched on the subject. A lot of the sort of change in shape that you observe on the outside of a body is like it's the muscles moving underneath the fascial layer, and then or the fat shearing. And those sorts of things together sort of have the cumulative effect of allowing you to sort of see these shapes moving under the skin. And like there are obviously some parts on the body where that's where you can really see that kind of what people would describe as skin sliding. But it's not really. It's more like it's the relationship between the fact that you have like skin, which is quite a stiff material, over top of fat, which is it's a very soft volume conserving material which can shear easily, and then underneath that there's that sort of fascia sort of pockets around these muscle groupings where the muscles can then move freely underneath the fascia, which is itself like sort of puts the muscles under tension, because the fascia is kind of like almost to imagine it like a super tight wetsuit that's sort of put on over top of the muscles, and it sort of keeps it helps keep everything together on your body. So without that, you'd kind of fall apart. So that's that, and for us, like the way we represent that in Ziva in our tool set is we have a like we'll model the fat, like so we'll do you'll have your skeleton, your muscles all simulated. Over top of that, you'll have a layer which we use to represent the fat, and on the inside of the fat layer, we put a material, with like a Z material just on the inside, which has both surface tension and pressure. And what that does is it sort of sucks that inner surface of the fat tightly against the muscles, and then tries to minimize the surface area. So the muscles can move underneath it, but it kind of squishes the muscles if you're running them as a coupled simulation. And so it emulates the physics of what is happening in a real body. It's obviously a simplification, but it's at the kind of degree of magnitude that we're interested in for characters and movies and games and stuff. It does a good job.
I see. So basically, it's the same solver, but with a very specific configuration and modeling, so you can achieve the results that it's very, very close to reality. But again, it's a simulation, so it's not gonna be 100%, I guess. But yeah, it's gonna. I mean, nobody will know the difference, I guess.
Yeah, it works. I mean, if you look at some of the results that we've had, like the lion example which was on our website. I can let me see if I can find that. Bear with me one sec. I'll just go back to here, and then I'll move the Skype window over. And see if we might have some. Actually, you know what? While we're chatting, I could just have the reel maybe running in the background. There'll be some examples on there that probably make sense.
Yeah, and now that we are looking on the website also, maybe it's a good moment to talk about the other product, that is the characters that you have. So you
sure.
have already you was explaining all this stuff that you need, like the modeling and so on, but you also have like a mini zoo of digital animals right now.
Yeah.
Well,
So as a company, like our teams kind of we're like cross-disciplinary. Half the team are software developers, or like when I say half the team, I'm referring to the people building product, not obviously administration or sales and marketing, that sort of thing. But half the team's focused on writing software, and then the other half are character TDs essentially. So we have 3 full-time in-house character TDs that we want them to hit all the problems with the software before our customers see it. So and a lot of these assets are the result of us building assets internally first and making sure the software can do everything we want it to do for our customers to achieve the results that they want. But it's actually been also a good sideline for what we're doing, especially since Anatomy Transfer was released in 1.6. So we've had a lot of people come and purchase the horse, for example, or back. The lion is, if you buy a license of Ziva Vfx, you have access to the lion along with the Cheetah external mesh for anatomy, so you can play with doing anatomy transfer from one to the other. But we've had a lot of people purchasing horse recently. I guess there's a lot of movies that need horses. So
yeah, I think animals, I mean, a horse is a horse. I mean, maybe the race is different and the proportions change, but yeah, it's very, it's not going to be completely different if you need a horse.
Exactly, and the anatomy transfer tools make it easy. If you have a horse of different proportions, you can warp over all of the geometry and all the rigging information from one character to another. Then you're off to the races. To excuse the horse pun.
And I'm just saying now here you have the layers. So I guess the B is bones, the M is muscles, the F
Yeah,
is fascia, the S
skin. I guess.
skin.
And P is for puppet. I think. Yeah, it's puppet.
Puppet means the control rig to
Yeah, like
to animate
yeah.
it.
So in the case of I guess the lion here, it doesn't come with a puppet, but instead we will ship it with some animation on a joint hierarchy, so you can drive it that way.
I see.
But yeah, so that's the character asset sort of side of what we're doing. We do expect to build this out more over time, but yeah, it's a small number of assets right now. And yeah, all of these ones have been focused on as Ziva Vfx assets. But in the future, with the release of some of the newer products that we'll have next year, we'll sort of cover more of the spectrum of character creation needs, from being able to build control rigs to being able to run your simulations, or then take your simulations and then make them run in make the output run in real time, but look like your offline simulation.
Oh,
So that's sort of the spectrum of things that we're working on right now.
that's really nice.
Yeah, I can jump over maybe to show the puppet. So recently we released this Ziva character demo, which involves Cheetah Puppet. So you'll see here, like, it just looks like a typical Maya puppet, and that again is on purpose, because we want everyone to be able to adopt this easily and not have to reconsider the way they think about what they're doing, at least in version 1. But what we do is we've made it run really fast. So if I hit play on this, so I'm running this on a laptop here, and I'm screen sharing and running Skype, but like it's without any of that other stuff going, it's usually well over 100 frames a second on this computer. So the reason for the speed is that we've taken over all the computation for the puppet. So what you're seeing here is not a Maya mesh. It's we're drawing it ourselves in the viewport. So it's like a custom shape that we're drawing. And then if you look at the rig itself, let me just select this so it's easier to understand what we're looking at. So I'll go into the node editor and view the up and downstream. So this is the puppet, is this node here. So that's the whole puppet sits inside of this. The things on the screen left are the control curves that feed into it, and the ones on screen right are basically, well, a lot of these decomposed matrix nodes will go away in Maya 2020 now that they allow for direct matrix connection, so that'll be nice. And then, but most of these outputs are for parents of controls that need to behave in certain ways, like if you're doing space switching or stuff like that. So that's what these are all for.
Yeah, I was thinking to ask about that. So
Yeah.
great you touched the topic. Yeah, because if you have like foot inside K something, so probably you need to move something down or reverse to the hierarchy. So that's the outputs that you have. Okay.
Yeah,
Cool.
exactly. Yeah, so inside of this, we have our own compute framework that we're building this with, and this, you can kind of think of this Cheetah asset, which is a free download from the website. It's kind of like a movie teaser, but it's a software teaser. So what it means is next year, anyone will be able to build their own assets that run this fast. And the way that you build it is we have our own CPU, GPU compute framework, which we call ZOA. So it's for Ziva Open Architecture. And it's a plugin based framework that we've written for ourselves, which is it's built to be able to compute things really quickly and we're making the process of creating characters as user friendly and as powerful as possible. There's certain bottlenecks and just pet peeves that we have with the current set of character tools that exist out there, regardless of which DCC you're talking about. And this will kind of represent our answer to that problem. Mm-hmm. And when you build your character in Zoa, then you'll be able to play back or interact with your character in the DCC of your choice once we have integrations written for all the different DCCs or game engines. So it's like a one stop to make stuff, and then you can deploy it wherever you like.
That's really nice. So basically, it's called Zoa.
Zoa,
It's gonna take care of the puppet behavior and the character deformation.
That's right.
That's nice.
Yeah, so or at least the first version, like the first set of features that we're releasing for Zoa, take care of that. And then over time, Zoa's capabilities will grow because it's a plugin based framework, and the way that we extend the functionality of Zoa using the plugin API is the same way our end users will eventually be able to extend it themselves once we publicly release the plugin API.
So the plugin API is gonna be like C++, or it's gonna be like Python, or you have something like a nodal based something, or how it's gonna be?
So we currently write our nodes in C++. We do have Python bindings for being able. It's a at the end of the day, it's a processing graph. So you can assemble your graph either in Python, or we have an early UI right now that it's still when this goes public, then like it will be a full application that you'll be able to do everything with. But it's you can write your own nodes using C++. You can connect nodes together with Python. We'll look to have some just-in-time compilation stuff in there to make it easy for people to go in and just extend some functionality without having to commit to getting into C++ and getting your environment set up and stuff. And we'll likely support Python nodes as well, though obviously it's kind of the user beware, because you might hit some performance challenges with Python.
Yeah, of course. That's understood, that Python always it's gonna be slower than if you do it on C++. But yeah, it's really nice. I mean, if you have something that you have just-in-time compilations and things like that, it's amazing. You can iterate really, really fast and do changes and see what you're doing over and over.
Yeah. So yeah, it's kind of like as a product, it sort of sits between like what you would normally think of as a DCC and a game engine. It's kind of between both of them because it allows you to package up these high performance characters.
So I guess the initial deploy is gonna be Maya, but it's open to another DCCs.
Yeah. So we do have a Maya plugin now, and we have a kind of a early implementation of an Unreal plugin for it as well. But yeah, the goal is to make this available everywhere. We've even deployed actually aspects of it on the iPhone, like just for because it is like what's cool with the framework itself is it is really lightweight, and it only eats up as much memory and compute power as the plugins that you have loaded. So in the case of doing linear blend skinning and IK, that's you can compute that on a smartphone pretty handily. So it's pretty neat.
Yeah, especially if it's a new iPhone or a new like smartphone, they're really powerful.
They are really powerful. Yeah. So
no joke. Well, yeah, that's really nice. I mean, I have like now you open the Pandora's box, because I have like million questions. I guess I can not ask everything now, but it looks really, really interesting for me as a rigger. That is my bread and butter every day. These kind of solutions are always like a I don't know. I would say something like very, very appealing and very like a treat for us, because it's yeah, for us, like, we always fight with like performance issues and things
Hmm.
like that. Not always to solve the what the rig is needs to do, and the deformation needs to do, like in terms of appealing, and they have their controls and the behavior that the animators need. But also you need to deal with all the technical sides of the evaluation and the performance.
Hmm.
And well, to be honest, I'm really happy with the current development of Maya, with the
Hmm.
new like animation cache,
Yeah.
playback, and also with the parallel and the GP overrides. I mean, there's a lot of fronts that are improving, but in for my experience, or what I try up to now, any of the solutions reach what I'm seeing with your demo here on this character. I
Hmm.
mean, these 100 frames, even if it's a very, very simple rig. I mean,
Oh, actually, I didn't show you. This we're kind of showing off a little bit, but you have to dig in this to see it. So this
mhm.
is the mesh that we're solving. Or oh, this is the wrong mesh. Oh well. I thought the example that we ship is using a mesh which is 666 or 645,000 vertices,
Mm,
and it's just basically kind of to show off that it's super fast even on really heavy meshes. So
mhm.
this one here that I have open doesn't seem to be that one. This is a lighter mesh, but oh well.
Yeah, it
But
must
yeah,
be like double. Yeah, I think I saw some screen capture somewhere
yeah,
on, probably in the website, or
yeah.
the little video you did, the little, sneak peek, I think, video.
Yeah, yeah,
Yeah,
that's
so probably I saw it there. Yeah,
yeah. But
that's really
yeah,
nice.
no, for sure. I mean, like all that stuff. Maya's been doing, like Autodesk's been doing a good job lately of trying to um, you know answer some of these demands of end users. I think we sort of have the advantage of being able to look back on the way the character creation process has evolved over the past 20 years and
Hmm.
start fresh. So like when I got started doing this sort of stuff in the early to mid '90s, anyways, there wasn't a set of like there wasn't this notion of like this is how characters are done. You just sort of you sort of put stuff together and you kind of made a character, and that's
Hmm.
still I think to a very large part the way a lot of characters are still made today. Like there's no real rules. It's there are ways that practices that people have
Hmm.
adopted because they realized over time, oh, this is a good thing for this and this is a good way to solve that. But it's still more like a big box of tools, and then you use them a
Yes.
certain way in order to make a character, but there's no character making thing. So we sort of have the benefit of being able to look back on the way that people have worked over the past 20 years, look at some of the bottlenecks that we hit because of the choices, or maybe the lack of choices, like the flexibility that
Hmm.
exists in the current thinking around how you do this sort of stuff, and then optimize our tool set in order to make the character process itself easier and faster to do, and then more performant as well.
Yeah, I agree with that. But yeah, it's very, like, yeah, I think, well, how do you see this is gonna evolve in the future? How, like, from your point of view on, like, this like 20 years experience, how do you see the future? Where on the character, digital characters, the rigging, and all the character effects?
Well, I mean, characters are becoming more and more involved in every facet of your life, right? If you were to imagine, back in 1990, in the early 1990s, like with after Terminator 2 came out, or Jurassic Park,
Mm,
you probably wouldn't think that people would be doing Snapchat filters of animated things. Tracking onto their face in real time, and that's essentially like character technology that's being used for that purpose.
yes.
So, like character, like all the box of all the sort of capabilities that represent characters are going to become more and more involved in our everyday life. So that the having worked in this industry, and everyone who's working in it right now sort of gives you the opportunity to get a sneak peek at the future in many ways, which is kind of cool. So yeah, like that's and then as far as like how the process is going to change, I imagine like what our goal is. Anyways, I can't really speak to what everyone else is doing, but our goal is to make the process, get rid of a lot of the drudgery in it, make it as quick as possible for you to get to the point where then you can start making your artistic choices, so that you don't have to waste all of your time just getting something working. You want to get to like 90% or more right away, and then spend all your time going from something that looks, really good to being great.
Yeah, I think that's it's gonna be remove this technological barrier where it's super hard to learn the software, or to like it's gonna be more artistic driven in some point. So I guess like especially and on the I think and that's my theory, but especially when it goes for things that are real that you can get the influence from the real world. I think it's gonna get more artist friendly than probably things that are maybe more not based on the real world, that then maybe it's gonna be more technical than before. Like for instance, for the maybe it's it's like a strange extrapolation, but for the before, to make like a modeling of something that is super realistic, like a building or something, it was more difficult than do like something that is like more like a cartoony building or something like that.
Yeah.
And nowadays with the technology, with all the scan of photogrammetry technology and everything, it's easier to extract the information from the real world and process with a very complex like algorithms and software to get the final result. So, and it's very artistically now. It's very easy to get that. Then if you need to model that maybe more like something that doesn't exist in the real world, it becomes way more complex. Because
I find like with I think more and more like at least where our opinion is on this sort of stuff is we want you to be able to transfer everything you know about the real world and then just apply it to what you're doing in the computer. Like, so Ziva Vfx is like an example of that. Like, people are familiar with the way objects behave when they drop, or if it's a soft thing, how it's going to splat a certain way. And if you kind of think of making characters, if you were to make a character out of real meat or whatever, it's you kind of think of it in physical terms, and that kind of simplifies the process a lot, because it's no longer a weird esoteric bit of dark knowledge that you have in order to you're familiar with all the crazy stuff that people have to do to make things look like they're real, but they're anything but. Like, you'll have your blend shapes feeding into your front of chain object on your skin cluster and all that crazy stuff that you have to do, but none of that has anything to do with real life. It's just a way you're trying to fake something.
Yes, exactly. So I think you articulated much better than me, but that was my point.
Exactly. Yeah.
That's a real meat. And indeed, we are looking at this horse right now in the loop, and I'm just paying attention to little parts, and it really, it feels like I don't know. It's if I lost it, it looks like a real like peel horse running.
Yeah. Well, that's the goal.
I don't know. It's cool, and at the same time, I'm still feeling like it's a bit like a horror movie or something.
Or Westworldy, I guess.
Oh yeah, well, exactly.
I can hit play on this. Do you get audio at all? Not that you need it, but I don't know if you get
It,
audio when.
no, I don't hear the audio here. I get
Oh, that's
yours, but
oh, okay. No, that's fine. Basically, like this is a demonstration of the rest shapes feature that went into 1.7. So this is also sort of on this path that we're on to try to make things as easy to use. So there's this notion of being able to use what you're familiar with in the real world and make things like they're made out of real objects. But sometimes you just want direct artistic control to say, I want it to look exactly like this. And that's what this rest shape feature lets you do. It allows you to be very specific about what you want something to look like without having to sacrifice all the nice stuff that you get with the physics. So if I were to fast forward to him, he sculpts the bicep to look like that there, and
so
then
that
he can tell the simulation that when it's solving to look like that. So I'll just let it play from here, so you'll see the arm bend and the muscle flex.
it's like the kind of a goal for in a specific position, like
Yeah, it's like a goal. It works pretty differently. Like what's really neat about what we're doing is we're blending the plastic strain energy. So what that means is, like in that elephant example that you saw right at the beginning of the video, when its trunk curls, that's only one. It's like there's the elephant with a straight trunk, and then there's a modeled elephant with a curled trunk. And when you turn on the rest shape, the trunk will curl itself up. It's not like a blend shape where it'll just sort of go through itself until it's a curled shape, but it's because we're adding plastic strain energy in order to make it curl up, which is a really neat kind of behavior that you get when blending things in a different space.
So basically here, for instance, the way that you will do it is you do this let's say range of motion, for instance, for this arm here.
Yep.
And you go to the key points that you want to are direct, and you specify like this is the volume, this is the shape I want, and this specific position.
Yep.
And then you let's say bake this shape information back to your solver in like the solver language of the volume and how it should behave to get the rest pose that you model, like
That's
in a more traditional way. Let's say.
Right.
So it's retrofits one to another.
Yeah, and what it does, like because we're doing embedded methods with the way our TET meshes work, that's why it's actually was quite a challenging feature to write. We have to do a solve to fit the TET mesh to your sculpted shape, and then on top, then we run our dynamics on it. And if you have a bunch of sculpted targets, we can pre-compute all that and up front so that it'll make it run really fast. But you can also plug a deforming mesh into it, and it will refit it live every time step. It just will be a little bit slower because it's doing this live solve to do the fitting before it runs the dynamics.
I see. And the way how you trigger that back, I mean, it's the solver itself who knows the position. You have like some kind of RBF or something that says this is the position that I want to trigger this specific volume.
So there is, you see there's on the Z rest shape node, you can think of it just like a blend shape node. So you end up with a bunch of parameters for the rest shapes that you want to drive, and then you can drive it however you like, whether you're going to use a set driven key or an expression or an RBF node or what have you. We'll likely ship with some of that extra control stuff in the future. I mean, we have internally, we have our own ways of doing that. It's just not all of our internal approaches are what we would consider, commercial ready. So it's more, it's fine for us to use, but it's not, when we make commercial software, we want it to be really solid, and it needs to meet a certain quality bar before we ship it to our customers.
Yeah, I was saying also in the video now your tetrahedros mesh.
Yep.
That it's getting the deformation super strange. Not strange, but you have these points that kind of explode or
Yeah.
going far, like here, for instance. But this
Yep.
is the way that the solver gets to the position that you set from the shape back to the solver. No, that's
Yeah, like the what the tet mesh looks like is kind of irrelevant because
oh.
you never use it. I mean, what this is doing though, like what's important is what the embedded surface looks like. So in this case, the tet mesh is exploding out like that because the way the shape was sculpted has forced the tet mesh to do that, to drag the embedded surface to meet, match what you want it to look like. So that's kind of why you get that. You do also though have some extra fitting parameters on it, so you could adjust your smoothness iterations, and that'll remove some of those spikes, but your fit to your sculpt might not be as tight.
Yeah, well, I didn't. Maybe no, it's not explode the right word, but but
no, I wasn't taking offense to it. I was just describing what the software is doing. Yeah.
But yeah, because the shape at the end, it looks nice and clean. So it's
Yeah. So this is like the live
the live.
connection here.
Nice.
And we've had customers already use this in rigs being used in production, which is pretty neat. Like where they've done live connections from traditionally rigged things and then plugged them into the solver. So now they get they can rig stuff, but then get all the physics on top of that, which is kind of neat.
That's really nice. Yeah, and I guess the solver is mainly used for muscles and body deformation, but I guess you can apply it to many situations.
It's a general purpose elastic solid solver. I mean, we use it for muscles and fat and skin, but I mean, we've had customers use it for couch cushions and like shoe rubber and whatever. Like it is just a finite element based elastic solid simulator at the end of the day.
Cool. Okay, so I think we just hit close to 1 hour. I don't know, on the so going back again to the ZOA, so you expect to have like next year, like it's gonna be on beta, or if the people want to reach you, or how it's gonna work,
Yeah, we'll go into beta first, probably a closed beta early on, and then depending upon the reaction of that will kind of determine how long it's in beta and determine when it becomes fully commercial. If we follow the similar kind of timelines and use cases of what happened with Ziva Vfx, the beta cycle for that was about 10 months in total, but it started being used in real productions about 4 months into the beta program. So I imagine, if we're on a similar trajectory, we should see the same sort of thing, and I imagine it will be used for real film productions next year.
That's cool. Yeah, for sure. When you open for the beta, I will apply.
For sure. Yep.
That's gonna be. It's gonna be like one more let's say passion project to learn.
Cool. Yeah, we want to I mean, and obviously like the early release, it'll be missing a lot of the functionality, which is eventually going to have. But yeah, we're doing a big push right now on getting some of the most of the core functionality in place, and then getting the beginnings of our UI in place as well, so people can at least work with it somewhat, like just as a standalone application.
Yeah, that's sadly what I'm doing right now, it's more like an anime style thing, so I don't know if I will have opportunity to use it in production, but for sure.
Yeah.
Maybe yes, because yes,
they
get actually quite heavy, the rigs.
Yeah. Here is also, that resolution of the Cheetah. I thought
I
had in my
that
scene
was
there.
the one I was thinking about.
Yeah. So it this sort of shows the kind of the expected speeds.
That's really that's really impressive. And do you try with multiple objects? Like it's one
Oh,
big object right now, or I mean, I guess.
so yeah, right now it's so this is sort of comparing the same rig done in Zoa, or compared to what it would look like in Maya, because we built the same puppet in both
Mm,
platforms, and this is and then as you add more puppets, then you sort of see more benefits because you can run so this is like 19 million vertices running. You can still scrub it and do stuff and animate without having to cache anything.
yeah, that's really nice. Especially I see the playback maybe goes down to 10 frames per second, but when you touch one of the rigs, the manipulation, it's super fluid. It's still like 70 or something. I was
Yeah, and
watching that.
if the puppet weren't more than 500,000 vertices, it would probably still run back almost at real-time rates. But yeah,
Yeah.
no, that's kind of a silly example.
And maybe it's too early to ask these questions, but it's gonna support like the basic kind of like approach on the deformation. Like you have like this on the SOA, like the linear skin and probably blend shapes and I don't know, Ziva Vfx. It will be also running under the.
No, so yeah, in the initial release, it's just focused on puppets and
Mhm.
focused on speed. So the what will be in there, we have our own IK solver. Like we have like a two-bone IK and spline IK solver, and that'll get extended over time as well. We have linear blend skinning, and then we'll have a few other deformers in there. I'm not sure which set of them we'll have yet in the first beta, but basically you should have everything you need to be able to make like the standard kind of puppet that people would typically use.
Mm.
But maybe some of the more esoteric deformers won't be in there yet. But yeah, right now, but as it is today, yeah, we have these IK solvers. We have a bunch of different constraint, like all the different constraint types that you need
Mm.
to build stuff. And yeah, it's just the basic components needed to make puppets, but they'll just run really fast.
Cool. Okay, so yeah, I think for the moment I don't have any other question. Do you would like to add something else on like where? Well, I guess the people knows where to find you and at zivadynamics.com.
Mhm.
Do you want to shout out some other like directions or places where they can find you?
Well, hopefully, in the movie theater, I guess. We're fortunate. Like a number of the films that are up for the visual effects Oscar this year used our
Oh,
software in it, so that was kind of cool.
oh,
Yeah, just please, yeah, if this is of interest to any of you, sign up, download an evaluation if you haven't used it at all, and follow the tutorials, and hopefully you like it and you get, it helps you to make your best work.
thank you so much.
Yeah, my pleasure. Great chatting.